Okay, welcome to the NUPOC video study guide number 87. Let's look at a chemistry problem involving a half-life of a radioactive material. So this problem actually, what it's telling us to do is to give an example of a differential equation that's used in chemistry and then to go ahead and solve that differential equation. So if we have a radioactive material, right? Like if we have a pile of it like this or a stick of it, we know that after one half-life, whatever that is, whether that's 10 years or a year or 10,000 years, there'll be half of it left, and after another half-life, there'll be another half of that, etc., 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 right? And it slowly decays away. And so the rate of decay actually depends on the amount of the material that's left. And we can describe that behavior with a differential equation. So stating what I just said in math, using a differential equation, we can say that the rate of change of the amount of material, or dq dt, is equal to minus rq. And Q is just the amount of material left. So the rate of change of the amount left is related to this minus R, where R is a constant, and it's related to the amount that's left. And of course Q is decreasing, and this negative here means that the rate of decay is actually slowing down. So as there's less and less material, right, dq dt is actually getting slower and slower and slower. So anyways, if we want to go ahead and solve this, right, first, like we've done with a bunch of our examples in the differential equation section, we're just going to make an assumption about the form of Q, right? So Q, which is a function of time, right, we're going to say is equal to some Q naught, some initial value, times e to the minus RT. So that way when we take dq dt, right, we get minus RQ naught e to the minus RT. So this, right, from this previous line here, we can say this is again Q, right? That's Q of t, or just Q, right? We don't have to say Q of t every time. So this whole thing right here is just minus RQ, right? So we have the same equation we had before. dq dt is equal to minus RQ, and Q itself is this Q naught e to the minus RT. So what we want to find out is what is this R in terms of the half-life of the material, so that if we're given the half-life of the material, we can figure out how much is left after a given amount of time. Okay, so now what we can do is we can say, all right, well, let's go ahead and assume that, I mean, we don't know exactly what lambda is for, whatever material we're dealing with here, but let's assume we have some lambda. So we have some lambda, and that's the half-life, right, in years or minutes or whatever. So that is the half-life in terms of time, and we know that after one half-life, so when t equals lambda, so Q of t equals lambda, there will be Q naught, the initial amount, over 2 remaining, or if we started with Q naught, we now have half of that amount after one half-life, right? Okay, and so this also equals Q naught e to the minus R lambda, right? We're just subbing in lambda for t, right? Okay, whoops, this is Q naught, gotta remember that. Okay, so now we can go ahead, and if we just look at these two terms here that are equal to each other, we can divide both sides by Q naught, and we're left with 1/2 equals e to the minus R lambda. Now let's go ahead and take the natural log of each side. So we will have ln of 1/2, right, that's the same thing as saying ln of 2 to the minus 1, which is the same thing as minus ln of 2, and that equals ln of all this, right, which is, I'll just write it out, e to the minus r lambda, which is equal to minus r lambda. So what we have is minus ln of 2 equals minus r lambda. So now we can just solve for r and say that r, of course we can divide each side by -1 so the negative signs go away, and r equals ln of 2 over lambda. So we can say then that Q of t in terms of the half-life of the material, so this is the amount of the material at any time t that is remaining as it decays away over time, is equal to the initial amount Q naught times e to the minus, e to the, minus, of course it has to be minus because it's decaying, e to the minus ln over 2 over lambda times t, right? Or, we could redistribute this any way we wanted to. We could say e to the minus ln 2 times t over lambda, whatever. But so we can plug in any time t here and get the amount remaining at that time if we know the half-life of the material. So we'll go over an example of this where we actually find the amount remaining after some time, hopefully in the next video. But up until this point, I hope that was helpful. And as always, don't forget to click down here and subscribe if you haven't already, so you don't miss out on those upcoming videos.